we have talked enough about vectors. Now let's move on to matrix and tensors. Matrix is a two-dimensional array of scalars or one-dimensional array of vectors. Okay, and then this one is a column, or this one is row. Okay, and basically the matrix A is an element of this space. And we can talk about tensor to generalize the vector, scalar, and vector and matrix. Okay, and scalar is actually a zero-dimensional tensor, and the vector is one-dimensional tensor, and matrix is two-dimensional tensor. And we don't have the three-dimensional tensor and four-dimensional. We don't have the terminologies for 3D and 4D tensors. Okay. And given a matrix, then we have a couple of operations. First one is transpose. Transpose is simply just to transpose the elements. We already talked about this transpose operator for vectors. Okay. And in the matrix, actually, basically, it's the same thing. So we just reflect the elements diagonally. Okay. So if we transpose, then A1, A sub 1, 2 will go into this place, and A2, 1 will go into this place. And this one will go into this place, and this one will go into this place, so that we can get this one. And for those who are already familiar with the PyTorch, then let me tell you one critical things. In PyTorch, you have a view operator, view function. Okay, so let's say we have matrix A, and if the size of matrix is 5 times 10, and if you call view, and if you change the shape of this matrix, then it will change the shape. But this is not the transpose, it's different. Okay. And when we have a two matrix multiplication, then the transpose of this multiplication is actually transpose and multiplication separately. And the next one is multiplications. Multiplication, when we say matrix multiplication, it means this one. Okay. So this one is A and this one is B. A times B can be calculated in this way. So they might have different shape, but they have to have the same number here and here. So the number of column of A should be the same as the number of row of matrix B. Okay, then the result will be M and P here. And this one is matrix multiplication, but sometimes we need element-wise matrix multiplications, like when A is 3 by 2 and B should be 3 by 2. When they have the same shape, then we can have a matrix element-wise matrix multiplication. Element-wise matrix multiplication. In that case, we just multiply this one too, and the result matrix will be will have the same shape. And this one is actually multiplication of this element and this element, and this one is actually multiplication of this one and this one. So just element-wise multiplication. Okay, and then still we are talking about matrix here. And when we have a matrix, then there are a couple of more operators. And the first one in this slide, first one is determinant. So do you remember how to calculate the determinant of 2 by 2 matrix? A, B, C, D. Given a 2 by 2 matrix, then how can we calculate a determinant? It was AD minus BC. But then how about 3 by 3 matrix? and 4 by 4. So can we actually generalize these equations? So let's look at this one. This one says A times D minus B times C. Okay, so when we have a 3 element, a 3 by 3 matrix, then the determinant can be calculated by this. Multiply this one and this one and this one, plus multiply this one and this one and this one, plus multiply this one and this one and this one, and minus multiply this one and this one and this one, and minus multiply this one and this one and this one, minus multiply this one and this one and this one. Okay, so we can do this for D by D matrix too. So this one is actually generalized determinant equation, and the determinant of 2 matrix multiplication can be obtained by multiplication of 2 determinant here, and determinant of inverse matrix is actually 1 over the determinant of A. And the next one, trace. Trace is simple. Just add all the diagonal elements. Okay. And trace of A times B is actually trace of B times A. Basically, they are the same thing. If you're really interested, if you're curious, then you can try. Okay. And what is the rank? The rank is the number of linearly independent columns or rows. And for square matrices, full rank means the matrix is invertible, it is non-singular, and it means the determinant of the matrix is non-zero. Okay, so basically it's the same thing. Okay, so let me explain a little bit of these linear independent columns. Let's say in 3 by 3 matrix, 1, 2, 3, and 4, 5, 2, and 2, 4, 6. So this matrix is not full. The rank of this matrix is not full, because this column vector can be obtained by this one, not simply just multiplications. Let me explain this one. We have 1, 0, 0, and 2, 2, 3. So in this case also, the rank of this matrix is 2, because we can actually get this column vector based on summation of these 2 vectors. Okay, so if we can represent this vector based on the weighted sum of the other vectors, then this one is not linearly independent. Okay, so in this case actually the rank is 2. So this one can be represented by weighted sum of the other vectors, then just ignore that, and then this one cannot be represented by this matrix. So we have 2 linearly independent vectors, column vectors. That is the rank. Okay, so if we have 3 linearly independent column vectors, then this one is full ranked matrix, which means we can get the inverse of this matrix. Okay, and then it's non-singular. The determinant is non-zero. Okay, and the next one is identity matrix. I think you are already familiar with this identity matrix. In 3 by 3 matrix, identity matrix is this. Basically, the diagonal elements are 1s, and the other off-diagonal elements should be 0. Okay. And the inverse, A times A inverse should be I, and A inverse times A should be I too. And inverse of A times B is B inverse times A inverse. And A transpose inverse is A inverse transpose. And we can have this kind of complicated inverse matrix. You can try this matrix by yourself. Okay. And when we have a matrix, then we sometimes talk about the positive definite or pseudo inverse. Okay, what is a positive definite? Positive definite is defined. A matrix is positive definite. It means matrix A. Okay. A is positive definite when this is satisfied. So X transpose A times X is always positive for all X which is non-zero. Definitely, if X is 0, then X transpose A X is always 0. So when X is non-zero vector, then this is positive. Then the matrix A is positive definite. And semi-definite means we have equality here. Sometimes it could be 0, but it cannot be negative. Okay. So to understand this positive definiteness, we need to look at these polynomial equations, quadratic equation here. If A is positive, okay, then AX squared is positive. Then what happens? We can have this shape, right? Or this. So this one is convex. Okay. What if A is 0? If A is 0, then Y is bx plus c, which means just linear. Okay. There's no curvature. There's no curved area. It's just a line, straight line. If A is negative, then AX squared is negative, which means we have this shape equation. So if it is a positive definite, then in this case, we talked about one-dimensional space. So in general, if this is always positive, then let's say we are in the two-dimensional space. Okay. This one is x1 and this one is x2, and x transpose A x has some value, right? So if this one is positive, then in any directions, okay, so basically we have some shape like this. Okay, so in any direction we have this shape. Okay, and if we have equality here, then maybe some directions we have this shape, but some directions we have line. So we have something like this. So at this point, in these directions, it is a straight line, but in this direction, we have this shape. Okay. So when we have a second order equation like this, then x transpose A x plus bx plus c, then if you are confused, then you have to go back to these equations, which is familiar to us. So based on this equation, you can understand what this equation means. Okay, so you have to make a map. And what is a pseudo inverse? When the A is not invertible, okay, when A is not invertible, like A is not square matrix, than this one. Let's say y is ax. Okay, then x is the three-dimensional and y is two-dimensional. Then matrix A is not invertible. Then what can we do? So we multiply A transpose y is A transpose ax, and we multiply A transpose A inverse A transpose A inverse. Okay, so if A transpose A is invertible, then we can cancel these out. So this one is just identity matrix. Then we have this one times y is just x. Okay, so it looks like this one is inverse matrix. So given this A matrix, if we multiply this one, then this one is cancelled out. So this one is working as if it is an inverse of A when A is not invertible. So this one is pseudo inverse. Pseudo means actually pseudo is something like a fake, right? So it's fake inverse, but it is working as an inverse matrix. Okay, next one is the linear transformations. I already talked about this, right? So y is A times x. So x is n-dimensional vector and y is m-dimensional vector. And then this matrix A is m times n matrix. Right. And then what is the magnitude of y? So y's magnitude, norm of y can be calculated in this way. So we can replace y with A times x. Then you know how to calculate this transpose. So we have this. And what if A is orthogonal? If A is orthogonal, then this one is just norm of x. Okay, because orthogonal matrix doesn't change the volume at all.